Every single time you hit the brakes or roll down a window or even see that check engine light pop on, you're using this incredible hidden network. It's basically the nervous system of your car. So today, we're going to pull back the curtain and demystify that network, the controller area network, or as you probably heard it, the CAN bus.
Just think about this for a second. Your modern car has like 70 or more little computers. They're called ECUs, or electronic control units. They control everything: your engine, your transmission, your airbags, your radio, everything. So how in the world do they all talk to each other instantly without turning your car into a giant, tangled mess of spaghetti wiring? Well, that is the exact problem the CAN bus was created to solve.
And here is that brilliant solution. It came from Bosch, way back in the 1980s. They figured out a way to replace these massive, heavy, and complex wiring harnesses with a simple two-wire system. And get this, it's a multi-master network. That just means any device can start talking whenever it wants. There's no central computer acting like a boss telling everyone when it's their turn.
So how does this two-wire highway actually work? To get it, we've got to start at the most basic level, the physical layer. We're talking about the actual wires and signals that carry the whole conversation.
Okay, so this diagram shows you how any single component, or what we call a node, hooks into the network. You've got the brain of the node, which is a microcontroller, right? But it doesn't speak the bus language directly. It sends simple signals to another little chip called a transceiver. You can think of the transceiver as a translator. Its job is to take those simple signals and create the special electrical signals that the bus needs to understand.
And here are those two special wires we've been talking about, CAN high and CAN low. Now, this is the secret sauce. This is what gives CAN its famous immunity to electrical noise. See, instead of sending a signal on one wire and comparing it to the car's ground, CAN looks at the difference in voltage between these two wires. So if some electrical noise hits the bus, it usually affects both wires equally, which means the difference between them stays the same. The message gets through perfectly clean. It's an absolutely brilliant piece of engineering.
This image illustrates it perfectly. The bus really only has two states. When nothing is happening, it's recessive or idle. You can see both CAN high and CAN low are just sitting there at about 2.5 volts. But when a node wants to send a signal, it creates a dominant state. CAN high jumps up to about 3.5 volts, and CAN low drops down to 1.5 volts. And that creates a really clear voltage difference between the two.
So here's the absolute key takeaway. That idle recessive state, that represents a digital 1. And the active dominant state with that voltage difference, that represents a digital 0. And here is the magic rule that makes the whole system work. A dominant 0 will always overwrite a recessive 1. Seriously, burn that into your brain, because it's the secret to how the whole system avoids traffic jams.
Which, brings us to the next big question. If any device on the network can start talking at any time, how do you prevent total chaos? How do you avoid these digital collisions? Well, let's look at the rules of the road.
The answer is this incredibly clever process called bitwise arbitration. It's totally decentralized. The nodes figure out who gets to talk all by themselves. There's no traffic cop. The message with the highest priority simply wins the right to speak. And crucially, no data gets lost or corrupted in the process. Here's how it plays out. Imagine two nodes try to talk at the exact same time. They both start broadcasting their message's ID number one bit at a time. And here's the key. As they're sending, they're also listening. The very moment a node sends out a recessive 1, but it hears a dominant 0 on the bus, it knows it just lost. It immediately shuts up and just listens. And since 0 is dominant and lower numbers in binary start with more zeros, the node with the lowest ID number is always going to win.
And it's not just me saying it. As the experts at HMS Networks put it, the message with the lowest identifier wins. This system is what guarantees that the most critical information, like say a signal from your brake controller, will never get delayed by something less important, like you changing the radio station. Priority is literally built right into the message itself.
All right, so we know how messages win the right to get on the bus. But what do these messages actually look like? What's inside one of these data packets? Let's pop the hood and take a look. This right here is a standard CAN data frame. The easiest way to think about it is like a digital envelope. It's got a start signal at the beginning to get everyone's attention, kind of like a, hey, listen up. Then you've got the identifier, which is like the address and the priority stamp. Then comes the actual data, the letter inside the envelope. And at the end, there's a bunch of stuff for error checking, which is kind of like the signature to prove it arrived safely. So let's zoom in on the most important parts. You've got the identifier, which we know sets the priority.
lower number, higher priority. You've got the data field, which can carry up to 8 bytes of the real info, like your engine's RPM or the coolant temperature. Then there's the CRC field, which is a really clever mathematical checksum to make sure the data wasn't corrupted. And finally, there's the ACK field. This is a little slot where all the other nodes on the bus can basically say, yep, got it, and it looks good.
Now you're going to run into two main flavors of this data frame. Standard CAN uses an 11-bit identifier. That gives you over 2,000 unique message IDs, which is plenty for most cars. But for really complex systems, think heavy-duty trucks, construction equipment, industrial automation, there's extended CAN. That uses a 29-bit identifier, which gives you, well, a ton more unique message priorities.
You know, one of the biggest reasons CAN is used everywhere, especially in safety-critical systems like cars, medical equipment, and even airplanes, is because it's just incredibly reliable. And that's not an accident. It's completely by design. Let's look at some of these built-in safety checks.
So there are multiple layers of protection here. We already talked about the CRC checksum, that's a big one, but then there's this other cool thing called bit stuffing. To make sure all the nodes stay synchronized, the protocol has a rule. You can't send more than 5 identical bits in a row. So after 5 ones or 5 zeros, the sending node automatically stuffs in the opposite bit. If any node on the network ever sees 6 identical bits in a row, it knows instantly that something is wrong and it flags an error. It's such a simple but really powerful way to maintain data integrity.
For decades, standard CAN was more than enough to get the job done. But you know what's happened? Cars have gotten way, way smarter. They're packed with cameras, sensors, and huge infotainment screens. The demand for data has absolutely exploded. And that led to the next evolution, CAN-FD.
CAN with flexible data rate, or CAN-FD, is a really big upgrade. Just look at this table. The maximum data payload, the amount of info you can stuff in one message, jumps from a tiny 8 bytes all the way up to 64 bytes. That's a huge deal. And even better, it uses a flexible data rate. This means it can actually speed up and transmit the data part of the message much, much faster than the rest of it, which dramatically increases how much data can flow through the network.
And here's the most crucial part. It gets bigger and faster without sacrificing reliability. To handle those much larger data packets, CAN-FD uses even more sophisticated CRC algorithms and an improved bit stuffing method. The whole goal was to get more data and get it there faster, but keep it just as tough and reliable as the original. So, let's bring it all together. Why is this technology from the 80s stuck around and become so dominant? Well, it's efficient. It replaces kilograms of heavy copper wire. It's incredibly robust, shrugging off electrical interference. It's unbelievably reliable thanks to all those error-checking tricks. And because it's decentralized, there's no single point of failure that can bring the whole network crashing down. So, from its humble beginnings, CAN Bus evolved into the faster, bigger CAN-FD. But as we race towards a future of fully autonomous cars, which are, let's be honest, basically data centers on wheels, the demand for bandwidth is just exploding. The question engineers are facing now is no longer just how to make CAN even faster, but whether an entirely new kind of nervous system will be needed altogether. It's something to think about. Thanks for tuning in.